All right, guys. So we're gonna go over some basic unit circle trig identities. They're also sometimes called Pythagorean identities. And then double angle and half angle identities. There's not much like new trig that I'll be covering compared to your trig class. But remember, I'm going to emphasize what you really need to know to be successful in calculus. Okay, so it's more about like just revisiting things that you've probably seen in your past trig class, but like seeing it again so that you can get a better understanding, hopefully, of these things. Okay. All right, guys. So here's your one. Today's date is the 5th. You get your first name and your last name, your last initial. All right, so here I have two for you. So how, more like discussion kind of a question, but how can you confirm if the point 1513, 1213 lies on the unit circle?
Did you mean 15 or?
No,
Okay.
I did not. Oh, I said 15, sorry. 513, I think I saw 513 and 1213. Sorry about that. So how can you confirm it lies on the unit circle x squared plus y squared equals 1? And then think about that for a little bit, chat with your classmates, and then take it a little bit deeper and ask yourself, how can you confirm? How can you confirm it for a general point, A comma B? If I just give you a random general point, what is it? How would you know it's on the unit circle? What must be true? Still got some passing back some old warm up. Oh, does anybody have extra little warm up sheet? All right, think about it for a little bit, and then I want you guys to just check in with your classmates, and see if you guys have a similar idea or not. Okay, guys, so let me just have you turn to your classmates, just share out. Remember, this is more of a discussion. What are your ideas? How do you think you might be able to do this?
I didn't actually solve the problem. Answer the question. Oh, it's been, I don't know, I just did. Since science. So it's right on. And yeah, I was like, I think I squared that, but now that was basically. I did. Put it in the form.
Math works out.
Yeah.
That. So we use that, you know. The final answer. So what is that?
Like number two.
Or it's like, if it's like, also that it goes on the unit, or it's like, then that needs.
Those two should equal 169 plus one.
Yeah, like that's understood, that's then understood.
I squared.
Plus it's not, then
Squared.
it's fine.
I think it's.
Yeah, it
Oh,
doesn't
like
like
that.
5 squared, it's 25.
That should fall.
69, and then you add 169, so it's 169.
Plus the definition of the- Like that's when very like nine. And we start straight in the part.
All right, guys, so let's see. These two rows, anybody want to share out their ideas?
Um,
B, go for it. Sure, yeah.
I just plugged in 5/13 to the x1 and the 12/13 to the y.
So you plug in the x coordinate here, here. Then you plug in the y coordinate
Yeah,
here.
and then I simplified it, which came out to be 5/169 plus 144/169. That equals to 169/169, which equals 1.
Which equals 1, okay? And so that means that it satisfies the equation of the unit circle. And so this algebra, what does it tell you visually? What must be true visually? But it's on the unit circle. It's a point, it says point with some decimal or subtraction values, but those values actually lie on the unit circle. So in general, how would you do it for a general point?
They have to square into the line.
You plug them in, and if they square, right, this will lie on the unit circle if this equals 1, right? So for example, will this point lie on the unit circle? Algebraically, you just plug them into the equation. That's 1 plus 9, that's 10, that does not equal 1, so definitely it does not lie on it. Oh, good, all right, that's up your warm-ups. Good job, guys. Warm-ups are usually like those questions that look complicated, and then you're like, oh, okay. I think I was overthinking about it a little bit. Just fine. I get the same problem, it's all good. Okay. So we're gonna use this concept that you guys just told me how to confirm this. Oh, okay, here's a name. All right, so let's see what's up. So we're gonna go on section 6.4. So basic unit circle trig identities. Revisit some of the identities you saw in the past. Hopefully I'll give you some tips and other helpful things to help you out. All right, so let's see. So we have our unit circle that we've been playing with. Okay. Let's see, got my radius rotated at some angle theta. And there's a point on the circle. For example, this is one of those points somewhere on that circle. And we defined x to be the cosine of whatever this angle is of rotation. And we defined y to be sine of whatever angle is of that rotation. So whatever these these coordinates are, that's what we're defining to be sine and cosine. So does this point lie in the unit circle that I drew here? Yes, that'd be like the AB, right? So if that point lies on the unit circle, what do you know must be true algebraically about this x coordinate and this y.
But then put this ratio is equal one.
When you square them and add them, they better equal 1. Because they lie in the unit circle. So since xy is a point on the unit circle, we have that x squared plus y squared is equal to 1. But what is this x in terms of trig? Cosine. So we're going to substitute the x with cosine instead. So this is equivalent to saying that cosine of this angle, when I square that, and when I plug in y and I replace it with sine of theta, that better be equal to 1. Okay. But normally, actually, this is a big notation thing. Okay. This is written, what's the word, like shorthand notation for it is cosine, and you put the square here. Does that look familiar? And then sine squared, and you put it there, and then that equals 1. Yeah, that one. That one is the most used trig formula in my opinion in calculus. Okay, it's like the mother of all the other ones. Again, this is used everywhere. So you have this trig identity. Okay, this is our first one, which means that no matter where you rotate the angle, no matter what angle I plug in here, as long as it's the same angle, if I get cosine and I square it, and then sine and I square it, that will have to equal 1. Okay, question?
Do we have to put cosine and sine, theta in parentheses, or is that just?
Actually, WebAssign is picky.
Okay.
You guys are gonna have, you can't just write, you won't be able to just write this.
Okay.
Okay, you do, and actually I'm okay with that.
Yeah.
Because I want you guys to start remembering that these are functions. That you plug in something and it outputs a number. Okay,
But what is sign with this is parentheses?
but WebAssign, in terms of correctness, wants you to put the parentheses. Okay, just be careful. Okay, now this equation gets manipulated a lot. Because as we're going to see today, we're going to be dealing with a lot of identities. And it's going to be like a big puzzle where you're going to have the left-hand side of one equation and you want to manipulate it to turn it to the right-hand side, right? So sometimes you're going to want to express one of these trig functions in terms of the other. And so, for example, if I wanted to isolate cosine squared by itself, what would be your first algebraic step to get this guy by itself? I would subtract that one. So then this would produce cosine squared theta equals 1 minus sine squared theta. And then that way I can rewrite, whenever I see a cosine squared, I can then remove it and replace it with 1 minus sine squared theta. So think of like algebraic substitution. Okay. Or I can isolate this guy, sine squared, and instead subtract the cosine one. So then I can rewrite this. And you guys will see how that's going to be used as one. Dang it, Siri. Let's see. Addition and subtraction identities. Okay. And so then from this one, you guys will be able to use these two so that you can swap something in terms of cosine with now only things in terms of sine. Okay. And there's more. Okay, there's more that we can do. Yeah, question.
You can also make the 1 minus sine squared theta and just cosine squared theta.
Correct. So if somewhere where you're going to see that later, you have all this trig stuff written on the board. If I identify a 1 minus sine squared theta, I can then replace that with cosine squared. So you can go forwards and backwards. Okay. All right, there's a little bit more. So let me rewrite this identity. From here we can get more. So here what we did is we subtracted things, right? But now what we could do is we can divide by things. Okay, to bring in other types of trig functions. So, for example, if I want to bring in secant into the picture, okay, what's secant the reciprocal of?
Cosine.
Cosine. So what I could do is I can get this equation and manipulate it by dividing everything by cosine squared. And let's see what happens if I do that. So there's 2. We're going to get another 2. So if I divide everything by cosine squared, I divide this guy by cosine squared, and then I divide the sine squared by cosine squared, and I divide the 1 by cosine squared. This becomes 1 plus, let me write it this way. See how they're both being squared? What I can do is I can write it as sine over cosine, and then that whole thing is being squared. You guys see that? Is that okay? It's going to end up being tangent squared, yeah. Here I can do the same thing, and I can write this as 1 over cosine theta, and that whole thing's being squared because what's 1 squared? 1, and cosine squared is cosine squared, right? But by me doing this, this now becomes 1 plus tangent squared equals secant squared. And so then now we have another trig identity where I can rewrite a secant squared in terms of 1 plus tangent squared. Okay. So by dividing this equation by everything by cosine squared, I got this identity. So what else could we have divided it by? Sine squared. Okay, let's see what happens if we do that. So let's get our cosine, this guy, and divide that by sine squared. Divide the sine squared by sine squared. And divide the 1 by sine squared. All we're doing is manipulating here. All right, here, let's be careful. This is just cosine theta over sine theta being squared. All right, if I square this, I get that. If I square this, I get sine squared. Big fat 1. And what's, or hold on, let me do this. This is just 1 over sine squared. Now, keep in mind, I allow a note sheet on the exam, okay? But when you guys take a calculus class, and I'm not teaching it, you don't know if your instructor will allow notes on the test. So you might have to like know these off the top of your head, okay? So just be careful. Like depend on the notes, but also like know that you should also kind of these ones that I'm showing you today, I'm showing them to you on purpose because they're used a lot in calculus, okay? All right, what's cosine over sine? Cotangent squared plus 1 equals cosecant. Yeah, the reciprocal sign is cosecant. And so this gives me another trig identity. Exactly, yeah. And if I want to get tangent squared by itself, then I minus the 1 and so on. Okay, yeah.
And if you square root it, you would just get the cosine?
And if I square, exactly, yeah. So there's a whole bunch of stuff that you see that can be done, yeah. But I think these like are the core ones that then you can manipulate as needed. Does that look familiar to some of you guys? Okay. I'm going to show you a little diagram that a student showed me in my calculus class that kind of puts all this together. Okay. So that's why I love teaching, because I always learn things from you guys as well. So here's a helpful diagram. So this is all captured on the following diagram. I don't know if you guys have seen it or not. So we're gonna draw a hexagon. I'm gonna draw a nice little hexagon. And that. And in the middle, we're gonna put the number 1 and then connect it to the corners of that. We're gonna start with our famous sine theta and cosine theta. And then on the left, we're gonna put tangent theta. That. Okay. And then across from those trig functions, you put the reciprocal. Across from them, you put the reciprocal. So what's the reciprocal of sine? Cosecant. Reciprocal of cosine. Secant. And reciprocal of tangent. Cotangent. Okay. And then this diagram. All the triangles that are facing down, that are pointing down. You shade them. And the way this diagram captures what we just discussed is all the triangles pointing down are these trig identities. They correspond to these trig identities. So sine squared plus cosine squared equals 1. Tangent squared plus 1 squared, which is 1, equals secant squared. 1 squared plus cotangent squared equals cosecant squared. So that's kind of like the little diagram. Across from these are the reciprocals. So that if I multiply this times that, it equals 1. If I multiply sine times cosecant equals 1. If I multiply this times this, it equals 1. Okay. And a trig function is the product of the 2 adjacent trig functions. So if I multiply sine with cotangent, what's cotangent? Cosine over sine. The sine cancel and it gives you cosine. And so that's true everywhere. If I multiply these two, it gives me cotangent. If I multiply these two, it gives me cosine, and so on. Yeah, that was cool. I wanted to share with you guys. Helpful. And that's all. It's also on the notes. Okay, just all that on the notes. Okay. So, with these trig identities, you're going to answer all kinds of questions. Okay. Some questions will be, if I know sine theta of, if I know one of these trig functions, you'll then be able to figure out all the other trig functions just by knowing one of them. Okay. And then, of course, the identity stuff where you have to prove stuff. Okay. Questions on these? Yeah.
So are all those supposed to be squared? I have a squared
No.
because these ones here have the.
They are, yeah. So the upside down triangles correspond to these trig identities. Yeah, they correspond to them in terms of their squares. The left squared plus the right squared equals the bottom.
All right. Oh, yeah.
So if you want to maybe like write like a little right, corresponds to left squared plus right squared equals the bottom squared. That helps. Okay, so let's see. So let's actually use these now. And we ran out of board space, so I'm gonna have to do. And then I'm gonna have you guys do a little bit of work. Example, bless you. After the break, can you guys remind me to reference something on the homework that people are having troubles with, the difference quotient stuff?
Yeah.
Just remind me to,
We're gonna have to be in class.
after the break, remind me, I wrote a note right here. Do that, but I forgot. Okay, but let's see, so, let's take a look at an example that you'll see similar to your homework. It says, given cosine of theta equaling -5/13 for theta being between pi and 3 pi/2, find all other trig functions at theta. Okay. Give you some time, write that real quick. Please remember to keep in mind where this angle's at. Okay, well, let's draw a little unit circle on the XY plane. Which quadrant are we in?
Three.
We're in quadrant 3, correct? So we're right, somewhere right here. Quadrant 3. Okay. All right, so let's see. So I know cosine, right? And that means that somewhere on the unit circle, that x coordinate is -5/13, right? So let's use our trig identity. Which of these three that we discussed uses cosine? The first. Cosine squared theta plus sine squared theta equals 1. So I would start there. I'm told cosine is -5/13, right? So I'm gonna substitute -5/13 in for cosine, but then I have to square it. So I plug -5/13 in here, and then I square it. And then I can use this to solve for sine. Let me wait. Does that make sense? Does that help? Okay, don't forget the squaring part, okay? So let's see, that's what, 25/169, the sine squared. And so then what would you guys do from here? Drop this sucker over here. 25/169, so that it cancels. And so this becomes 169/169. What is it? 144? 144/169. You square root both sides, and then you gotta consider what happens when you square root both sides. Plus or minus 12/13. But then you're gonna use the fact that theta lies on the quadrant 3. Sine is supposed to correspond to which coordinate? The y coordinate, which is negative in the third quadrant. So then it really is going to be sine equals -12/13 because theta is between pi and 3 pi/2. Okay. So here's the beauty of all this. As long as you guys know sine and cosine, that's it. You know everything from there after that. Because tangent is in terms of sine and cosine. The reciprocals are all in terms of sine and cosine. Okay? So as long as you can find what cosine and sine are, then you just use the rest of the identities. So tangent, that's just going to be sine over cosine. Yeah. So then that's going to be -12/13 over -5/13. Becomes, yeah, you do multiply by the reciprocal, and then it becomes +12/5. because tangent can be written in terms of sine and cosine. Secant is written in terms of cosine, which I already know. 1 divided by -5/13. Or what's the reciprocal of this bad boy? This is the reciprocal, right? So it's just -13/5. Cosecant theta is the reciprocal of sine. So it's 1/-12/13. What's the reciprocal of this bad boy? 13/12. Is that it?
Yeah.
Cotangent, cotangent. Cotangent, you could do it different ways, okay? You can say it's a reciprocal cosine over sine, or just say it's a reciprocal of tangent. So if it's a reciprocal of tangent, yeah, so it's 1/tangent, which is just 5/12.
How'd you get 12/5?
This is really -12/13 times the reciprocal. Like that, so then the 13s cancel.
Wouldn't it be?
It would be positive because the negative turns a negative. So that this homework has a lot of points because it's gonna ask you for all the trig functions of this. Okay. I really want to get into the proving trig identities though. That's the hard, the ones that students have a hard time with. For these, you're gonna start by using one of these trig identities. And as long as you can find sine and cosine, that's the magical ingredient, okay? I think this is like the first, maybe like first 3 or first 4 of your homework problems, they look something like that.
Before we move on,
Yeah, before I move on.
on Monday, like, I wasn't there, but I was watching the lecture, and I was seeing like you were using some way to determine whether like sine is 1/2 and cosine is square root 3/2, or vice versa, and you were using some like, if 1/2 is like greater than square root or less than
Oh.
3/2. That I
Yeah.
didn't quite.
Can I help you during the break on that? Okay, yeah. Yeah, I know what you're talking about. Which one's longer to determine if it's root 3/2 or 1/2?
Yeah, it was.
I know exactly. All right, guys, so. This is one type of question where you use these trig identities, but the next ones are proving equations are identities. This is where the fun stuff comes in. Next week, when you guys come back, we're gonna be solving equations with trig. But to solve those equations, you need to be creative in terms of which trig identity you're gonna use. So this is training you for that, right? All right. Sorry about that. You're both Gomez.
Yeah, 144.
Right here?
Because you subtracted 125.
No, I subtracted 1 minus 25, 169.
Oh.
So I converted the 1 into 169 over 169. And then 169 minus 25.
And you can say 1 is actually 1 is here, right?
You can set 1, well, you can set 1 as 1/1, but you need a common denominator, which turns out to then be that same number over itself. All right, guys, so let's take a look. We're gonna start a problem, but then pick it apart as much as we can, and then ask as many questions as you want, okay? Because you're paying money for the class. Don't forget. Yep. So you guys have every right to ask all the questions you want. All right, so prove that the equation is an identity. And let's see, we're gonna do this guy here. Sine of some angle B over 1 plus cosine of that same angle B plus 1 plus cosine of B over sine of B, that better equal 2 cosecant of B. All right, and let's just stop real quick and reflect. The hell is going on? So when you guys are, when you guys see, I think the reason that students get confused by this question is because up to all the math that you've done now, when you're working on a problem with an equation, you're solving for a variable. Right? You're solving for X, or you're solving for theta, or you're solving for Y or something. The reason this feels weird is because you're not solving for the variable. What is the variable here? What is the unknown? B, the angle B. We don't know what the angle B is. There's, if the question said solve for B, then what it's asking you to find, it's asking you to find what is the angle that you plug in here that gives you equality on both sides. That's what that question is asking you to do. But this is not asking you to do that. It's actually telling you that it's an identity, and that means that this is true regardless of the angle. There isn't just one angle that makes it true. It's any angle that I plug in will make it true. Okay, we'll make it so that both sides are equal. And that's what the difference is between, that's what it means to show that the equation is an identity. Is that it's true for every single angle B. You're not solving for B. So don't think that you have to solve for B. That would be really hard actually on this problem. So instead they're asking you, use trig identities to show, somehow conclude that this left-hand side can be rewritten logically into the right-hand side. Okay? That's a different question. That's a different question. But the thing is that solving for B, if it's an identity, B can be any angle. There are an infinite number of solutions. Yeah. So let's see. So to organize this, we're going to call this, usually your textbook will say the left-hand side. And then this we're going to call the right-hand side. Okay. Tips. Okay. Usually it's helpful to start with the more complicated side because there's more things you can do with it and turn it into the simpler looking side. So that way you know where to start first. If both sides are pretty complicated, that's a different example. We'll look at more of those, okay? But in this case, it'll be helpful to see how can I manipulate the left-hand side and use all the trig identities that I've learned, not all, but use trig identities that I've learned, but at the same time, algebra that you guys have learned, like factoring or adding, getting common denominators. Like you still use the algebra tools that you learn, but then you're also bringing in trig identity. That's why these are hard, because it's like a combination of both of those things. So let's see. So I'm going to start out by, let's just say, okay, what is the left-hand side going to be? It's this whole thing here. You don't have to rewrite it, but I'm going to rewrite it to show you the flow of it. So I realized that I'm adding, I'm not multiplying. If I was multiplying, that'd be great.
Yeah.
It's like cancel, 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 cancel.
Fine.
Done. But it's, you know, it's
Just give you two.
yeah, but it's adding, so I can't do that. Say it again.
Wouldn't that just give you two?
That would, oh, if it was multiplying,
Yeah, wouldn't that be two?
it would be 1 over 1.
Oh, yeah.
Yeah, so it'd be 1, but it's not that. It's addition.
Maybe next time.
Yeah. So what I want to do is maybe just start with what the algebra is telling me to do. I have to add. So I need a common denominator, right? Right now we're not using trig identities at all. We're just using algebra. Okay, so in the algebra, I know I need common denominator.
As I sign E,
I would want, what do you want your common denominator to look like?
so 1 plus cosine B times sin C.
I want eventually my common denominator to have both of these pieces. Okay, so that I can add them. That's kind of where I want to go.
What minute is it?
If
Because I guess they still wouldn't be the same, because they would be a separate.
well, it would be like if I said, what's 3 plus 5? I can't just turn this into a third. Like the logic in terms of this is 8. I can't just,
Let's make it 9 over 3.
I could make it 9 over 3. Yeah. But like, I think what you're saying is like, why can't I just make this a reciprocal?
Yeah.
It's for this, like, when I'm adding things, I can't just make that a reciprocal like that. Yeah,
It's the addition property.
yeah, it's, if there was like a equation and I wanted to multiply by both sides by a reciprocal, that's different, yeah. Yeah. So if I want my denominators to be a common denominator like that, this fraction needs to be multiplied top and bottom by sine of B, and then therefore I have to multiply the top by sine B, which will get me there, yeah.
So
But-
I have to multiply that by the 1 plus, oh wait, that is the addition, or the denominator, mine.
Gotcha. Yeah, that's already there, right? Versus this one is missing the 1 plus cosine B. So we're gonna multiply this other fraction by the other factor that I want, which is 1 plus cosine B. 1 plus cosine B. Okay? When I do that, now I'm gonna have common denominator. I'm gonna have, but as a consequence on the top, what do we have? Sine
Sine squared.
sine squared, good. Sine squared B over that denominator that I wanted. And then plus, here I gotta be careful. Is it just cosine that's multiplying there? No, this whole thing is gonna multiply with the whole numerator. So I have to FOIL it out. Okay? You guys see that? It's just algebra right now, right? We're not using any trig identities, it's just algebra. So 1 times 1, 1 cosine B plus another 1 cosine B is 2 cosine B plus cosine squared B. All over that common denominator that I want. And just kind of rearranging these like that. I'm moving them so they look the same.
Aren't you allowed to just go in and multiply?
Why can't I just do this right here?
Why can't you?
Yeah, because sine B over sine B is just 1.
Oh, okay.
And a number is still the same if I multiply it by 1. Yeah. This over this is again just 1.
Okay.
Yeah. All right, so then let's see. Now I have common denominators. So now this whole thing will be on top. So sine squared B plus 1 plus 2 cosine B plus cosine squared B is all over my common denominator. Sine B. And I'm running out of room, so I'm gonna waste this side. Okay. So then you stop and then you reflect a little bit. At some point, you want to bring in trig identities, right? Like to make things a little simpler. Yeah, do you guys see a cosine squared here and you see a sine squared there? There's a trig identity that uses both of those, right? Cosine squared plus sine squared is supposed to equal 1. So what I'm gonna do, you could do that in the next step, but let me just organize it. I'm gonna rearrange the numerator so that you guys can clearly see it. I'm gonna move the cosine squared to this side. Like, I'm still adding it though. I'm just kind of rearranging the top
You're putting it in the order of the like coefficients.
of the, I'm putting them in the order of, so you can clearly see the trig identity. Okay, I'm just rearranging it so that now you guys can see this guy here. According to my first trig identity that we did, what is this supposed to equal? Cosine squared plus sine squared is supposed to equal
1.
1. Okay? So then this guy just turns into a 1. Okay? And then I add the rest, plus 1, plus 2 cosine b. And then I guess I'll write it. And then now I can add the 1 plus 1. That becomes 2 plus 2 cosine b. And then you guys see how they both have a 2? There's a 2 here and there's a 2 here. So what can we do with that 2? Factor it out. Common denominator. Take a look at it. 1 plus 1 gave me this 2. Okay. But now there's a 2 and a 2 that can get factored out. Okay. So in that next step, I'm going to do that. I'm going to factor out that 2. When you take that 2 out, you end up with 1 plus cosine b all over 1 plus cosine b times sine b. What is if I multiply the 2 back in? What's this guy? And then beautifully, look what happens. Yeah, 1 plus cosine b is the same, top and bottom, so it can all cancel out. And then you end up with 2 over sine b. Okay. From here, let me see how, yeah, question.
Yeah, how come you don't need to FOIL the denominator?
Oh, good point, good point. So most of the time when I'm adding things and I'm eventually trying to simplify something, right? You don't want to multiply the denominator because you're hoping one of those will cancel.
Mhm.
Yeah, kind of like when we were doing difference quotients. You didn't want to factor out the, multiply the denominator, hopefully hoping that the h would cancel out.
Mhm.
Remember?
Yeah.
Other questions? Yeah.
How did we go from 1 plus 1 plus 2 plus sine b?
How did we get this guy? It came from, when I, here, let me go like this. Let me go like that. This one came from this trig I did, right?
Yeah.
Okay, then I added these 2 ones. When I added those 2 ones, I just got a 2.
And you distributed this one.
And then I pulled out, kind of distributed, but I undistributed, like I factored it out.
Yeah.
Yeah, so I took this 2 out to give me that value. Yeah. Okay. Other questions, clarifications? Yeah.
If we were to rewrite like on our test, and like we ran a time visit, like, so instead of writing sine of b, you do sine of theta, so it's easier for your brain to look at. And you write the final answer with the b, is that okay?
Oh, like if it just do all the work with theta?
Theta instead of b. If the letters get kind of confusing.
Yeah. Yes,
Data, not the food. I'm just like.
sure.
Okay.
Yeah. On every sign, just make sure you put it back with B's,
Yeah.
for sure.
Yeah.
But also train your brain to not always have thetas there, because later on you're gonna have just other things like compositions of twigs and stuff.
Just like
LNs and
also
shit.
with Math, so like the less letters. the better.
Agreed. I mean, right now, that's not the point, right? Like, it doesn't, it's irrelevant.
Exactly.
Yeah.
You don't solve it.
Are we done?
No.
We're not done. What are we trying to get? This side to equal. So what would you guys do to help you turn this, like, what? You know, maybe you see the cosecant there right away, but if you
I
don't,
would
what?
write out the right side.
Say it again?
I would write the right side as 2 times 1 over sine.
Exactly, yeah, this here is really 2 times 1 over sine, right? So can I write that as 2 times 1 over sine? Let's see. What's 2 times 1 over sine?
Oh, yeah.
This, I can, so this is, let me bring up a good point, so maybe I'm stuck there and I'm not sure where to proceed. So then what you could do is you can manipulate the right-hand side and be like, okay, what can I turn this into? This can turn into 2 times 1 over sine B. And then you can say, oh, look, that's exactly what this would be. So then you just put that in that step. Okay. And so finally, I'm running out of room. You go here now. This is just what? This is cosecant B, which equals the right-hand side that I wanted. So then you're done. Right? These are hard because there's algebra with trig identities, both playing together. That's why they're hard. Okay? Or challenging.
I think more tedious.
Tedious, yep, but I think if you're still like a little rusty with the algebra stuff, that's where it can be like a roadblock. So did we solve for B?
No.
You did not solve for B, right? That's not what this question is asking you to do. You proved it and it proves, and that's another reason you guys are uncomfortable with it, because you're proving something. So in math, when you prove something, there's usually a statement that you're trying to prove. And you just use each step is a logical mathematical thing that you do that is equivalent or it can be derived from the previous step that eventually connects one idea to a different idea. So if you end up taking like linear algebra and all that higher level math, you will be doing proofs. And this is like the type of thinking you do. You start with one thing, and then you say, what can I do with that that's mathematically, logically okay to do with it? Kind of like the discussion we were having, or I can't just flip that like that, because that's mathematically incorrect. I can't just do that. But I could combine this by common denominators. That's mathematically okay. I said, eventually, you keep doing that, and then you get stuck. You're like, crap, I'm stuck. I don't know how to proceed. So this is why math can be fun. Because you have to get a little creative sometimes. And you have to be like, oh, I can think of this as being the number 1, and it's okay if I multiply it by 1. You know, so that's where there's a lot of creativity. So if you guys, I'm just gonna nerd out now. So when you guys transfer as a math major, there's 2 routes that you can take. There's the applied math major and what's called the pure math major. The pure math major, they focus on only pure theory, not applications of the real world. And so they get their bachelor's degrees, it's a bachelor's degrees in arts. Versus if you do applied math, it's a bachelor's degrees in science. Okay? Because pure math requires hella creativity and a lot of like thinking and not so much application. Yeah.
Isn't that once you get into like the PhDs and stuff, it gets into like ethics and stuff like that somehow?
It can, definitely. Yeah. Because then it's a, say it again?
You got your arts.
I did pure mathematics, so I got my degree in I got a Bachelor of Arts and a Master of Arts. So I'm an artist.
It's
Math is
certainly,
definitely easier.
Say it again?
It's a little easier doing like arts major than. Well, not when you get to math. We did
gnarly. It's abstract art.
It's very abstract.
Yeah, it's not. It's not like English.
It's different. Yeah, it's different for sure. But your homework becomes pretty much essays. Writing proofs.
Wait, so
There's a-
English is not.
Because it gets more complicated, so you have to explain to the reader your next step. So you have to actually write things. I like switched to math because I was like, oh, I hate writing essays. And then I got here, I'm like, fuck, all I'm doing is writing. Okay, guys, so let me give you guys one. We have you guys try it out and then we'll take a break. Oops. Practice. To prove the equation is an identity. All right, so we got 1 plus sine theta times secant theta plus tangent theta equals cosine theta. Check it out. Make sure you write it correctly too, okay? This is gonna get weird. So usually start out with just the algebra. Start out with the algebra, manipulate it algebraically, how you think it should be. And then if it's not taking you anywhere after that, then see if you can bring in a trig identity. Also helpful if you write things of sign in terms of sines and cosines. Is that what you're gonna say?
I was gonna ask if that's probably just start right.
That's one thing you could do. That's another helpful tip is, let me just turn everything in terms of sines and cosines. Okay?
Is that also like ended over here?
Yeah, if this example went like that, I ran out of space and then I came here. Thank you.
Would you flip it to something? Say it again? How would you flip secant to?
Well, so secant equals 1 over cosine.
Yeah.
So you would just rewrite, instead of writing secant, I would just rewrite it as 1 over cosine.
Yeah, oh, the denominator is.
Don't hate me, guys. That's supposed to be minus.
No, man. Yeah.
Makes a lot more sense.
Yeah, sorry.
Okay.
Okay. Sorry, that's supposed to be a minus. Here I am telling you,
Now I-
make sure you copy it right, and I didn't do it. Hopefully that makes it easier. Comments on the exam. Triple check everything.
I know. It probably doubled. Oh, I didn't know this. Oh, okay. This. This one. This one. I know this is.
Against the moon,
It's a little bit, you know.
That's exciting. Maybe it's right, but I'm not.
You guys can't check with your classmates, confirm things.
You get co-sign data.
And this is for talking about, so I'm ready.
But no, it's so much more immediate when it comes to this kid. Well, I'll read it out in my favorite.
Yeah, yeah, it was like.
Yes, parts of that. All that you can do is match it down to what this is. Oh. So what number assigned for assigned? So it's. I got it. Gotcha, we can restart, so I got it. This is not about this.
Oh, March. It's like STEM or what? It's STEM and then it's minor or STEM, but like also.
Yes.
You can get a lot of people, that's good, so. My double major. That's why I'm deciding how do I some of this. Something science, but like, it's not, I want to be like, it's something that program, you know. It's. I like this side. Like, it's just needs. Same thing, after college, what
So see how you did. And now
that like, it's not, it's hard to work with these, the environment over there. Yeah. No, like, it's not a ridiculous, like, you're just using nothing. Well, both of us, not him.
Look at the top.
That's what he said, yeah, I know that, I know that my friend, her name is Jenny, he also goes to Hudson. Yeah. It's like a chill environment, yeah.
All right, guys, let's finish it up. It's beautiful. Walking around, people were doing it different ways. That's fine. That's the beauty of a proof. It's how you want to make your argument. Okay. So I did see most people just start by rewriting this as sine and cosine. That's kind of the common thing I saw. You could have also just FOILed these out.
Yeah.
That's another way you could have done it. That's fine. Okay. They both are going to require you to FOIL. You guys want to FOIL first? Or turn these into sine and cosine? Okay. Let me beat them. All right, that's it. Let's keep going. Let me. Okay, so secant, you guys rewrote it as theta plus over cosine theta. Good. Now, technically, it's like the logic doesn't follow. You're trying to show that the left-hand side equals the right-hand side, right? So it doesn't, like just writing this on the side is like mathematically incorrect because you're saying, oh, it already equals cosine. You're trying to show it equals cosine theta. Don't write that there yet. We're not there yet. You got to earn it. Okay. Okay. So then from here, see how they both have a cosine? They both have a cosine. So then I can add the numerators since they have common denominators. So that becomes 1 plus sine theta. Now I can write it all over the same common denominator. And then I think here's where most people were stuck. Okay. Realize that this is over 1. So I can multiply the numerator with this numerator and then this denominator with this denominator. And so this just becomes 1 times cosine theta. And this becomes, you got to FOIL it. You're going to FOIL this guy with 1 minus sine theta because they're being multiplied. So 1 times 1, 1 times positive sine, negative sine times 1, sine theta, and then negative sine times positive sine, squared theta. And then these suckers canceled out. Boop, boop. So you end up with 1 minus sine squared theta over cosine theta. Is there any more algebra?
No.
That's it. So that's why I was telling you, once you're done doing as much algebra as you can, most of the time, the next step is, oh, I need a trig identity sum. And then I realized this guy has the number 1 and it has a sine squared. So I use, we use this trig identity equals 1. And if I subtract the sine, notice that that gives me what's I have here. Okay, so then this can now be rewritten because of trig identity. It can be rewritten as cosine squared theta, because that's what this is supposed to equal over cosine theta. And then you cancel this out with one of these, and then now I earned it.
Yeah.
Now I got cosine theta. Okay. Another little mistake I saw was writing this as cosine theta. And I think you guys were thinking this guy, like you were thinking in that kind of realm, but you can't, these are squared.
Yeah.
If the sign's not squared here, then you can't do that, you can't use it. Okay? All right, before you go on your break, let me just show you something real quick. On WebAssign, let me show you how these problems are gonna look. They kind of help you. They're kind of guiding you. You just have to fill in the missing pieces. Okay? On the exam, it won't be like that. Okay? On the exam, I'll just say, show the left-hand side equals the right-hand side. And just the way you did it right now. Okay? So I think the problem set has a problem with that, so that you can practice doing it like that. But basically, you just have to kind of fill in the boxes logically, either algebraically, you know, like maybe I combine like terms and then I put that there, or there was a trig identity. Okay. All right. So let's go on a break. Come back at 2:10.
What day is 6.4?
Yes. We're doing 6.4.
What was the thing that you were wanting to remind me about? For the-
When you guys come back, we're gonna talk about, I'm just gonna quickly reference how to get started on these problems. Yeah.
Oh my gosh.
These bad boys. Difference quotients back. I need to keep grinding you guys in that because the calculus instructors are. Oh, I'm one of them, but yes.
I'm so sorry that I'm late. I haven't noticed.
Say again?
I said I'm so sorry that I'm late. I haven't noticed.
It's okay. I do not pass out a handout. Yeah, so you're fine. Okay. Oops, let me pause the recording. There we go. So let's say they ask you for like problem F. Problem F says find delta G over delta X. On the interval pi over 4, comma pi over 2. Does that look right?
Yeah.
Okay. So then what they're asking you to do is, remember, this is a difference quotient. They're saying the change in G over the change in X over this interval. That really means you're doing G. Remember when we were doing the interval A over B with the average rate of change? You were doing G of B minus G of A.
Yeah.
So here you would do G of pi over 2 minus G of pi over 4 over B minus A, which in this case is pi over 2 divided by pi over 4. Okay, but then you ask yourself, okay, that I know how to do this as a function. What do I do with the G? The G is supposed to be cosine. So that's really asking you to do cosine of pi over 2 minus cosine of pi over 4 divided by the difference of these two values. Okay. But then here you have to use your knowledge of the unit circle and how to figure out cosine of pi over 2 and cosine of pi over 4. And then continue from there and simplify it. Okay. So this is just the difference quotient. Same old difference quotient that we did on exam 1. Okay. Some guidance there to help you out. I can give it to today. Okay, let's keep going. There. Okay, guys, so now we're going to go on to section 9.2. It's going to feel kind of similar. But now this is more identities. Double and half angle identity. Also, very, very much used in calc, especially when you start doing something called an integral. Let me show it. Okay, so let's go over, let's quickly review some identities that you started with. These will be derived from another set of identities called the addition identity. Okay. So in your trig class, you learned the addition formulas. These are not used a lot in calc. Okay. They make an appearance like way later in your, or I guess they kind of beg and show it, but not as much as the double and half angle. Okay, so if I got sine and I'm adding two angles inside of it, unfortunately, it's not just sine of A plus sine of B. It's more complicated than that. Okay. It turns out to be sine of my first angle times cosine of my second angle. Remember that? Okay. Plus cosine of the first angle times sine of the second angle. There's addition and subtraction. Yeah. But right now I'm just going to use the addition. There's even more. Okay. And then for cosine, if I add two angles, what I can do is I can just know, I can know what sine of A would be and sine of B would be, and then it turns out to be cosine of my first angle times cosine of my second angle, minus sine of my first angle, sine of my second angle. Okay. And then in your trig class, there was a big geometric proof or a big geometric explanation of how this happens. Okay. Which we don't have time, but the textbook also provides that information if you want to revisit it. Yeah. Yeah. But it also uses a little bit of geometry to make more of the connections. Correct. So you derive these addition identities, but then to get your double identity, that means to get the angle 2A, this means I'm adding A twice to the top. So then we use these guys. I'm trying to think of my board space here. Nope. I'm gonna need more room on the bottom. So we're gonna use these. These help us derive the double angle identities. So if I'm trying to do sine of 2 theta of some angle being doubled, well, 2 theta is the same thing. It just means I'm adding theta with itself twice. It's just sine of theta plus theta, right? And then from this bad boy, I then use that addition formula to show me that this is just going to be, what's that, sine of theta times cosine of theta, since the angles are the same, plus cosine of theta plus sine of theta.
That's not sine 20, it's sine
2 times theta, not 20. Yeah, this is the Greek letter theta. That's representing an angle. And so therefore, this tells me that sine of 2 theta is going to be equal to sine theta sine theta, cosine theta, but do you guys see how this is also just sine theta, cosine theta? Because they're multiplying. So how many of these do we have? 2 of them. So then it gives me 2 of those sine theta, cosine theta. Okay. So here's your first trig identity. Or your first double angle. Yeah. This bad boy comes from this guy. And so then we do the similar thing, but for the cosine one. This one's gonna be a little bit, doesn't turn out to be as pretty. Well, kind of. 2 theta is just the same angle being added twice. So let's see, make sure I don't make a mistake. So this would be cosine theta times cosine theta. Plus or minus? Minus sine theta times sine theta. And so therefore I get that cosine 2 theta. Help me out here. How would you guys write this? Are these adding or are they multiplying? So what's it's squared? So it's going to be cosine squared theta minus sine squared theta. This one was 2 because these were adding, right? Not multiplying. So then I get this bad boy. Cool. Okay, but this one has more. Okay, why does it have more? Because it actually uses cosine squared and it uses sine squared, and those live in other trig identities, right? So what I want you guys to do is manipulate the right hand side by using this other trig identity that we learned from the previous section. See what you can do with that. So cosine 2 theta should equal something else if you take this approach. But if instead you took the other trig identity here, remember that one from the previous section? Right? I can rewrite sine squared. So if I rewrite sine squared theta as this, then what will that look? So I want you guys to figure out what are other ways to write cosine 2 theta using these identity substitutions that we're doing. There's 2 cases. One, I replace cosine squared with that, or I replace sine squared with that.
You can replace both.
If you replace both, you end up where you started. Because you'll get this minus this. So the minus ones will cancel. And then minusing a negative becomes positive. So it'll be positive cosine squared minus sine squared. So we go. Okay. But maybe like this one. So what are the 2 other ways that we can write cosine 2 theta? Because these are actually going to be the ones you're going to use more. Okay. And then just confirm with your classmates. Careful with negative signs. So what I'm asking you guys to do is to manipulate this right-hand side by rewriting cosine squared, for example, as 1 minus sine squared. Okay, and some people weren't, I didn't explain that clear enough. So let me show you what I mean. So I'm gonna get this trig identity. I can rewrite this as 1 minus sine squared theta. And then this is because of this identity. And then I just tag along the minus sine squared theta. But when I do that, what can I algebraically do now? I can combine these two together. And so this shows me a different trig identity. It becomes 1 minus 2 sine squared theta. Yeah. Because I was able to rewrite cosine as 1 minus sine squared. Okay. And then I guess I should have put an or here. Or I could have left this one alone. And instead replace the sine squared with 1 minus cosine. Back. Oh, here I have a negative in front, right? So we got to distribute that negative. So now what happens when I combine this with that bad boy? Yeah, I get 2 cosine squared theta minus 1. So this is a different trig identity. All three of these speak to each other this way. Okay. So what does that mean? That means that if I'm doing a proof and I see cosine squared minus sine squared, I can rewrite this whole thing as cosine 2 theta, or vice versa. Or I can rewrite cosine 2 theta as this. Or I can rewrite cosine 2 theta as this. You get to choose which one's going to help you. Hell of them. Right. So this one is the easy one because that one only has 1. Yeah.
Could you just use the top one and then your sine squared theta plus cosine squared theta equals 1 to get both of them? The bottom two?
Use this top one
Yeah,
to get, say it again.
and then use your cosine squared theta plus sine squared theta equals 1 to get the bottom two.
Well, this will stay sine 2 theta though.
Okay.
Yeah. Let me see what you mean later on. Okay. Yeah, because these better equal cosine 2 theta, not sine 2
Not
theta.
sine theta.
Yeah. But yes, as Koya was saying, that's where the hard part will come in. When you see a cosine 2 theta, you have 3 choices. This one, or this one. You have to figure out which one will benefit you to give you what you want. Okay. Okay. Then from these two down here, you then can isolate the cosine and you can isolate the sine. That's going to give you a different identity leading to the half angle. So let's take a look here. So what do I mean by that? Watch, let's write this guy here.
Wait, you said that you guys sleep in what text in the house?
These are all double angle identities, right?
Yeah,
Because of the 2 theta here.
but if we isolate the cos and the sine, you're saying that it'd be a half closer than.
Then it's going to lead to a different type of identity called half angle.
Mm.
Yeah, and so I want to show you how that works. So I'm going to grab this guy and let's get sine by itself. Okay, so to get sine by itself, algebraically, what do I have to do first? If I want to isolate the sine. What would you do if I had 5 equals 1 minus 2x squared? What would you do first?
Oh, dude. Subtract.
You would subtract the 1, right? So the algebra is still the same. So I would subtract the 1 to both sides. Yeah, let's subtract the 1 to both sides. -2 sine squared. And then what would you do? Divide by -2. And so this goes away, so I get sine squared theta. Here, I don't want to throw you guys off with what I'm gonna do next. But you guys see how this is a negative? I can also rewrite this negative in front of the fraction. Right? If I write it in front of the fraction. Oops. If I write it in front of the fraction. I can think of this negative like that. Which can then be distributed. So then it becomes negative cosine theta plus 1, right? That 2's still there, but basically I can rewrite this like this. But I just want to, I didn't want to just skip to that part because that's confusing. So this negative, when I distribute it to the top, it turns to cosine negative. Hold on. See, I got sloppy here and fucked me up. Cosine 2 theta, 2 theta, 2 theta, 2 theta. There you go. So I just, that negative goes on top, which distributes to these guys. So then I get negative cosine 2 theta, and then I get a positive 1. Is that okay? Question?
Would the 2 there be able to cancel out the 2 in the cosine?
No. It's kind of, this is function notation. So it's like if I
Okay,
did something like this, I can't just
Yeah.
cancel the 2. Yeah. All right. How do I get rid of that square? You can square root both sides. And then I get plus or minus, or actually, let me write it like this. I'm going to get sine theta is equal to plus or minus the square root of 1 minus cosine 2 theta over 2.
So in this like that, you gain like that, we get my answer and I want us to keep.
Say it again. What do you mean?
Keep going, that's first.
No, this is it.
Okay.
This is it. This is it. What the hell is happening, right?
So it's just like, I thought you needed to simplify too, it literally has sine theta equals something.
Me too, that's why I was like.
We're not proving an identity.
Oh, okay.
No, we're not proving. Yeah, what we're doing is we have this identity, right?
Mhm.
And so what I'm saying is I'm going to use this identity to get sine by itself to give me this equation. Why am I doing that? Because now this tells me that to evaluate sine of an angle, I can evaluate sine of an angle if I know cosine of double the angle. But the way the textbook is going to say it is they're going to say that they're going to say sine of half an angle equals plus or minus 1 minus cosine. What happens if I double this angle the way this angle is doubled?
It becomes just singular.
It just becomes a theta. Like this. Why? Because 2 times theta over 2, the 2's cancel. Okay.
What's the purpose of this?
What's the purpose of that? Great question. We're about to do in a little bit, but basically, you guys know how to do sine of pi over 4, right? With the unit circle. Okay, but do you know how to do sine of pi over 8? You don't know that yet. The unit circle didn't help us with that. But what this formula says, this angle is half of this angle. Right? If I divide pi over 4, and if I divide that by 2, that's pi over 4 times the reciprocal, pi over 8. So what this formula is going to do is going to help you evaluate smaller angles than we've been able to do. Okay, and that's where I'm going next. Great question. Like, why the hell are you showing me this? Similarly, guys, if I would have started here with this trig identity and solved for cosine, you would get a very similar thing. Okay. Notice how we trig identities, I apologize, but similarly, if I had, I'm not gonna do all the work. But if I would have started with this guy here. Oh, -1. And I do the same thing, and I isolate cosine theta. I end up with cosine theta equals plus or minus the square root of 1 plus cosine 2 theta over 2. And so in your textbook, though, they're gonna say, look, this is double of this angle. So then cosine of theta over 2 is plus or minus the square root of 1 plus cosine theta over 2. Now, let me go to your question now. So why are you showing this? And it has to do with what I was telling you about those angles. So on the homework, they're gonna ask you to evaluate. They're gonna say evaluate, let's do 2 of them. Let's do sine of pi over 12. We haven't done that. We don't know how to do that yet. Okay. Question.
So you do that,
Well, you want to ask yourself, is this, we know these special angles, right? We know all these special angles. So is pi over 12 half of these, half of one of these angles, or is it double one of these? It's half. Which one? It's half of pi over 6. So I don't want to use a double angle identity. I'm gonna have to use the one of these two. Right? And so, yeah, so it's this is really half of pi over 6. Right? You would use this trig identity, correct? Yeah, so this is half pi over 6. Okay, so what's in this formula? What's the theta that I'm going to use? Is going to be pi over 6. So according to that half angle identity, it's going to be the square root of 1 minus cosine. What is this half of it again? Pi over 6 over 2. But now I have to figure out, is it plus or minus? Is pi over 12, which quadrant is pi over 12 going to be in? In the first quadrant. So should sign be positive or negative in the first quadrant? Should be positive, so it's a plus 1. Okay. This is because pi over 12 is in, let's just say, in quadrant 1. Okay. Here you do have to simplify it. So I go and I have to figure out now, well, let me unit circle, what's cosine of pi over 6?
root 3 over 2.
Root 3 over 2? You okay with that? You're like, sure, I think so. Okay, it's root 3 over 2. Over 2. And unfortunately, you have to simplify that. So here, I want you guys to help me. What should I do? What would I do from there? What can we do? I'll deal with this two in a little bit. But what can we do to the top first? This one is 1/1, right? So it's really 2/2. So now I have common denominator, so then I end up with 2 minus √3
Over two.
over 2 over 2. So then this becomes this fraction times the reciprocal of 2, which is 1/2. So then that gives me 2√3 over 4. The 4 is a perfect square. So then I square root the top over the square root of the bottom to eventually give me look at this, square root of 2 square root 3 over 2. So whatever the hell that decimal value is, on the unit circle, when I rotate pi/12 radians, the y coordinate of that point is this nasty irrational number. Okay? And I couldn't have done this without the half angle. Yes.
How are we able to multiply by 1/2?
This is 2/1.
Oh, okay.
So I have this fraction dividing this
Okay.
fraction, so. So in the homework, you guys are gonna get some of those, okay? Oh, sorry.
No, it's perfect.
Sorry.
So that's the X.
It'll be posted too.
Okay.
No, they're all-
That will be the result of the X.
This right here.
No, wait, that's Y.
This, yeah, so let's see geometrically, what this means is on the unit circle. If I rotate my radius pi/12 radians. Sine is that y coordinate. So that y coordinate right here. Is that ugly number,
Oh, so sine pi/12 equals that.
equals that.
Oh,
correct.
okay. I lost track of that with all the numbers.
Yeah, sine pi/12 equals this.
I didn't know you can add the square of the as well.
You could have a square root and some square root.
It's the master.
It's just messy.
Lord, I'm scared.
I know. I know.
What is this over here?
Oh, this is just like a analogy of the algebra you had.
Oh.
listed.
What's the one I missed?
Yeah. All right, guys, so. You'll be using your half angle formulas to help you now evaluate smaller angles. But you will also use these formulas for proving trigonometry. Okay, so I want to spend more time on those. Yeah,
What makes it a half angle?
this,
Yeah, but like, what is a half angle?
like, oh, so we know how to evaluate these special angles. So we use this formula to evaluate the half of these special angles.
Just to simplify it?
Just to have an actual way of doing it, because we didn't know how to do it. Yeah, we couldn't do like the whole SOHCAHTOA, the unit circle, none of that was giving us how to evaluate the values. The only way now we know now is do this.
See, what happens when you have a number that isn't easily divisible into a number you already know?
Then we don't know how to do that yet. So there's more than you would do. Maybe another trick in here. But as much as all we'll need to know is the half.
Do we get into, do we have to learn that in this?
No,
Okay.
half angles are the ones I want you guys to focus on. All right, guys, so the last thing is again proving identities. Proving identities. Last thing we'll do, time is it? Stretch real quick. Okay, let's do a couple more. I'll do one, then I'll have you guys do one again. So prove the equation is an identity. So I want to prove that the left-hand side, which in this case is cosine of 2a, equals cotangent a sine of 2a. Ooh, I know. Brutal. So both of these are pretty, like you can manipulate both of these in this case. Isn't one that's simpler. Okay, or up to you, whichever one you think is simpler, but they both have multiple things going on. So I got my left-hand side here. And I got my right-hand side here. You guys pick. Which side do you want to start with? Right here. The right-hand side? Okay, let's start with the right-hand side. I'm gonna just rewrite it. Is there any algebra that I can do? Any adding, multiplying? Yeah. Yeah, just trig identity stuff, right? Maybe let's write everything in terms of sine and cosine. Cotangent, help me out. What's cotangent? Cosine A over sine A times. This is sine of 2a. So what did we just say sine of 2a equals? 2 sine A cosine A. By now turning these into sines and cosine, now is there any algebra I can do? What can you do? Multiply the top out? Yep, this is just over 1, right?
Yeah.
So this becomes 2 sine A times cosine times cosine A becomes cosine squared A over sine A. And then these suckers cancel. Yeah, that always feels good. So then I end up with 2 cosine squared A. Oh. Uh-oh.
So you won't always do the lesson, you or do more complicated stuff.
Whichever, this is an example where they're both kind of complicated, like they both have, they don't just have one term.
Yeah, but I find that one's easier because it's just like adding on, so.
Sure.
That's why we did it.
Sure, yeah, this one has a couple more identities, right? Yeah. Okay. So now I'm stuck here. We proceed. So here's an example where, okay, the easier parts of this took me up to here, right? And then I'm kind of like, I can do a whole bunch of things from here. I can maybe use another trig identity here. But my tip is if you're like, okay, I'm not sure how to proceed from here, pause it. And then now start from the left-hand side and see where that takes you. Okay, so I'm on the other side here. I'm gonna see, okay, let me just stop the right-hand side. It only got me up to here. Let's say instead I would have started with the left-hand side and see where that would take me. No algebra, right? There's no algebra to do, but there's cosine 2a, which has 3 different versions. So you need to decide which of those three, so that eventually it could look something like that. Take a look at those three that you learned. Which of those three identities can I replace cosine 2a with, so that it kind of has this
Minus one.
2 cosine squared a minus 1. Oh, look at that. Because now what? Yeah, the ones cancel. Now the ones will cancel to give me 2 cosine squared a. Okay. On the homework, I believe on web assignment, it has to do it like this. And then this is it, you're done. Why? Why? Because it's saying the right-hand side leads you to this. This is that, which then leads you to the left-hand side. Okay, question.
How did you get from the second step on the right hand side to the third one?
This one from here,
Wait, actually, no, the first one is the second one.
this one?
Yes.
So we rewrote cotangent as cosine over sine. And this was a double angle identity. 2 sine cosine. So there was no algebra. It
How
just,
does the double angle work?
that one we got from, when we were doing, sine of a plus a, and we derived this guy right here is equal this big identity. So we just replaced it, we substituted. So WebAssembly will have you do it this way. Okay, I'm also okay if you show your work this way, but in case you end up with future instructor, what you could do is you can say, okay, what can I do to this so that I go backwards? You literally can just rewrite everything. So I would just go, oh, this is equal to 1 plus 2 cosine squared and minus 1. Because these ones cancel.
So in this case, with this one, we're trying to find this.
You're still trying to show that one side equals the other side. Through like a process of steps, you're still trying to show that the right-hand side will eventually lead you to the left-hand side,
So.
or
this
vice
is
versa.
Basically just proving
Yep.
that this is.
Correct. Proving it, yeah.
So you would do the left hand side to see if you're on the right.
If there's a way, exactly, if there's a way to connect to see if you're on the right track.
Okay.
And there is, because this
is
led to
that.
this. So now to connect it, I just literally copy the work backwards.
Okay.
And so then this right here is the double angle identity. Cosine 2a. And there, I'm done. This is the left-hand side. Okay. This is more of like brainstorming to help me see what my path would be.
Yeah.
Okay. Can I give you guys one?
Yeah.
Try it out. And then I think that's it. Yeah. I think that's it. Okay, let's see. Try this out. Prove the equation is an identity. So sine of 2 theta over sine theta minus cosine of 2 theta over cosine theta equals secant theta. You be careful, you don't cancel. I see like means on this stuff. You can't do this, okay? You can't do that. So don't do stuff like that, please. Okay. This is a whole, yeah, whole thing, so be careful. And let me triple check that I wrote down the right problem. Hold on. Yeah, that's good.
So what I was saying as a tip is, which of these two sides is more complicated? The left-hand side or the right-hand side? Just start from there. So ignore this one for now. And then somehow you're gonna do this. Okay? Left-hand side. Mhm. So here there's different things you can do. One, you can start by already replacing these with the double invariants. Or you can try to combine like terms, the common denominators and add the fragments together. Depends. It'll be a little bit of trial and error. Okay? You think about these tasks, because you guys use it a lot, because it's lagging. You have to separate it. Okay, yeah, so you do that. You can't do this. Okay, these are all multiple. Okay, so now we'll do one side of well, this is the point. So that sign. Are you doing this one? And the sign is. So let's say you wanted to, subtract these fractions. No. Yeah. 2 times cosine squared. Well, can I just multiply?
So. Is that what you're doing?
Yeah.
I think I might have to.
I know, it's a lot, I just.
This feels more difficult than any of the others. So
But it definitely shows.
This one's harder, this one's harder, and there's multiple ways to get there. Because there's that, because of the cosine two theta. All right, let's see what's up.
Yes, okay, we're very good.
Combining that.
So what is the?
So the answer is here, you got two sine cosine.
Sine, cosine.
And then minus. Parentheses.
The denominator
Yeah, I
is
just-
just combined. Just sign. Say that goes out.
So it's-
Like, can you turn it into one big?
Oh, it's what
If you do that,
like that.
these two multiply.
Theta.
Cosine squared.
Theta.
Yeah.
And then here, this sine theta is sine here, and number one.
Thank you.
Sine, minus sine theta. And then you're gonna have a sine theta, sine theta factor. After See what happens?
Thanks.
Yep.
It's very versatile, not versatile.
This is similar to his, but then see what happens if you have guys look at each other, because even had together the same way. Somehow they look different, so. You multiply. You multiply this by cosine, remember? So cosine.
There's double.
Double and half,
Oh, and then it's this.
Should I give it?
yeah, well, it's those two and then the sign.
Oh, this one?
Yeah,
Everyone else.
I think so.
Okay, I see what you're doing. So this is,
I'm here.
Yeah, do not close it.
Yes.
I do, I just wanna
take out a sine theta from everything, but cancel it.
No, I don't mean that this is a joke.
Oh, no. That's not. Ah, this is because this actually the answer. Yeah, and this neighborhood, distribute here and the distribute here, so it's positive. So it's a.
I'm not sure if I can imagine. This is the identity from like the. I
Okay.
just put it in there, just, so I think that's what I have. to do.
Okay, so from here, yeah, all you can do now is you have to use the identity. So you don't want to write that this equals
Oh,
this.
yeah,
You just want to replace this with that.
so replace all of this?
No, you want to replace the sine two theta part
With this,
with that.
Oh,
Yes.
okay.
But to go down like this, like you don't want to go
Yeah.
this way. You want to go down.
Okay.
Rewrite everything, but
Okay.
instead of writing sine two theta, do it like that.
That-
And this one,
I would have to use the close one.
you need to figure out which of those three you want to use. Yeah.
I know.
Already changed, like, is that a year or just like figure this out first and then figure out which comes to the shop?
I'm just going through.
Yeah, you see how right here, the multiply these two together, and there's the two, cosine square.
Yeah.
So there's the two, and there's a cosine square. Yeah, so out of the three identities for, over here, out of these three, which one uses it, which one has a two and a cosine?
Yeah.
square?
And then these signs get.
So then that's probably the one.
that makes sense.
Yeah, that's so weird.
Yeah, this is where it's tricky, so, so see if you. Okay, you the question. In your brain, this is what you see, but you don't want to write that, you don't want to like invite people to something. What you want to do is you want to rewrite this with this. Meaning you would write.
No, you did. Yeah. Yes.
This, instead of writing that same people did it, you're gonna now write it as a sine theta, cosine theta,
Oh, okay,
times this cosine. That's what I'm.
okay,
Let's see, is that okay?
Yeah.
That's what I'm.
okay.
Now you gotta do this guy. Okay, cancel. Now you gotta do this one. So the question is. There's three of them. There's this one, this one, and this one. So you want to be strategic about what you want to do. If I was to multiply this together, this would be a 2 sine theta cosine squared theta. Right? And I'm going to be subtracting that with whatever I end up replacing this with. But see how this one has a 2 and it has a cosine squared theta? Which of these three has a 2 cosine squared theta? That one. So it probably will help you to replace the cosine theta with this one and not these.
Okay.
Right down.
That's -1 times.
Exactly, exactly. Yeah, you're gonna, instead of writing that, write the just.
Okay, thank you.
Yep.
Minus.
Oh, yeah.
How's it going?
Like, I got it now. I was thinking like combining like terms or something, or like eliminating like terms. Condensed. Yeah. Because this and this like term, cosine and cosine like term. So then it would just be 2 sine theta, cosine theta of the beta, subtract cos square theta like over that, but then there won't be anything at the bottom.
Oh, I was the one.
Oh. Also thinking like I'm going to combine like the family, right? Or like it's like something.
Are you on my own? So I'm gonna use it in like around and that's like.
Yeah. But then you gotta make more complicated. Where? But it's good to become the cosine square.
Okay.
Makes me feel today.
I love it. It's already down. I don't look at one.
Yeah.
Okay.
We do it, where it's like, it's short. You could. It's like
It's.
either like finding. Or like.
So we want to speak on this.
Seeking would be
Yeah.
The correct two.
fine.
Yeah.
Or is it clear?
Yeah, right.
It would be close, because that was a weird one.
Yeah.
That you were complaining about, yeah.
Yeah.
Yeah. Yeah.
Because the first thing goes for, trying for something.
Yeah. Okay. So that means that.
So we want to end up with,
I have-
because otherwise your child.
Yeah, because,
Okay.
Yeah.
yes,
Then we
that's
start
here.
with that.
Yeah, did I multiply by short line?
Yeah, they got stuck in the negative here, giant thing, so you're gonna distribute that negative. Yeah, because it doesn't feel good. That's not good, that's how.
Yeah.
That's.
Really?
It's more the way.
That's true. Well, you just, it's easier to solve than it is this.
So you want.
Bottom makes sense.
Oh, that's exactly what I'm.
Still separated. So you're gonna notice that you can actually cancel one out. So that's why it's hard to cancel it down here, like once you get to the. But if you can see here. I broke it into things like, you know, there's a lot of people. And. So there's only. Now. If you know,
Start here. I can just.
you can come down. So the two goes over the sequence. And then so it's two goes like that, one, and then you can pull up the two you can. That was my first, Up in there. No, it's not clear. I mean, yeah, 165. Especially when you get there. That's like three. I have.
Oh, yeah.
Well, I see. One minus science. Yeah, I definitely the credit transfer. I want to convert it, but I'm not gonna do it. Obviously. So it's like, if I want to switch to something else, back to.
All right, guys. We got 3 minutes. There's many ways to do it, okay? Yeah, yeah, let's do I think the longer one is when you don't do the identities first, but instead you try to combine the fractions. Let's do that.
Yeah. And write up the solution for
The other one, okay. Well, I have to leave like right away. I have a meeting, but okay, let's take a look. So we got sine 2 theta, left hand side, sine theta, cosine 2 theta. So what I saw folks do, harder one, meaning it just took more steps. And I think you guys started by adding, subtracting the fraction. So you multiply this by cosine theta. Cosine theta.
That's what I did.
Okay. And so by doing that, you now have common denominator. And then this right here, minus this, here you got sine 2 theta, right? So that's 2 sine theta cosine theta times another cosine theta, which is cosine squared theta. All over sine theta cosine theta. And then here is where you have to be strategic. Sine theta cosine theta. I'm gonna be lazy and I put the parentheses, okay? So here's where you want to be strategic. Which of the three do you choose from that one? And the hint is this, hopefully you can cancel something. This guy has a 2 and it has a cosine square. So it might be beneficial to use the one that uses a 2 cosine squared theta, which is 2 cosine squared theta minus 1. Which is, I think, if you do the other one, it would be longer. It's because you were using the other longer, right? The other one will get longer.
Yeah.
Which is fine, it's just a couple more steps. So then you distribute this guy here. 2 sine theta cosine squared theta minus 2 sine theta cosine squared theta. But there's a lot of distribution. Hold on. I'll write all this up.
You just go all of it under one.
You could put all of it under one, yeah, so then I can put all of this under the common denominator, right? But here you gotta be careful, there's this minus here, that's separating the
Do
fraction,
you distribute it?
so you actually have to distribute
And then it's
in here, which some people weren't catching. Yeah, I feel you. So when you do that, it's 2 sine theta cosine squared theta minus 2 sine theta cosine squared theta. But this becomes a positive sine theta. And then what happens?
Yeah, so like terms.
This cancels. And you end up with,
One of the cosine.
you end up with sine theta over sine theta cosine theta. The sine cancel,
One over cosine.
1 over cosine. theta.
Oh. That's crazy.
Other ways of doing it though. So good job, guys.
Yeah, for,
Are you thinking the line?
well, yeah.